Okay, hello everyone. My name's David Brimley. I'm a product manager for Elasticsearch. I'm based in London, and this is Henning Andersen from Denmark. I'm not quite sure whereabouts in Denmark, though, so you have to tell everyone.
I'm from a small city called Silkeborg in Denmark, right outside Aarhus.
Okay, great. You're going to be. Why don't you be in charge of that? Actually,
sure.
So we're here to talk about the future architecture of Elasticsearch, and really what is our journey to serverless. So we were thinking about what's the best way that we can talk about this subject of serverless and maybe inject some interest into it. And so we're both big David Bowie fans. So again, we're showing our age with Rod Stewart and David Bowie, but we decided we'd map each stage of this journey that Elasticsearch has made towards serverless against the backdrop of David Bowie's albums and his evolution. So this is really a story about data and how data increasingly has value if you can use it in near real time to change an outcome. So this could be a customer experience that is happening right now or augmenting data for downstream consumption. Now, our search and search in general is a pretty humble beginning. If we think about the sizes of searches and the data sets we were searching on, they might have been in the gigabyte ranges of data. So for example, a consumer-facing application like a product catalog or a hotel inventory where you were looking for your next holiday destination. So these search use cases required a bit more sophistication than a simple relational database could provide. So a generation of technologies was created to find a better and faster way of finding relevant results. And that's obviously where Elasticsearch came along. Now, as the data needs of the organization grew, with things like click streams, logs from Apache web farms, metrics from thousands of compute nodes, and observability data started to be collected. And then the challenge became, well, how do we find the needle in the haystack of all of that information? And with each of these generations, Elasticsearch continued to evolve in order to meet the users where they were, using search to drive the analysis of these new data sources. Now, as we enter the next phase, where retail companies have exabytes of logs, metrics, and other sorts of data, it's really required us here at Elasticsearch to think about how we can respond to those challenges, how can we architect for them. So looking from the outside in, what do you want, the community, our users and customers, what do you want from Elasticsearch going forward? Well, we're hearing from you that you need a platform where you can use data quickly and easily to solve the business challenges in front of you. But the most important thing is you want to spend less time figuring out the technology of Elasticsearch and instead more time using it to solve your new business problems. So you want to innovate in your business and problem domain, and you need that platform that innovates with you. Now, that could be doing hyper-personalization, search relevance for e-commerce applications, could be anomaly detection in a security use case. But you need those insights and results in near time. You want to focus on the business outcomes and not focusing on the infrastructure or admin tasks. And you want something that works regardless of what data you put into the system or the searches you perform. And it needs to be as fast as it is on a usual day as it is on Black Friday. And most of all, and importantly, you want to pay for what you consume. So that what you use one day might be what you use on a peak day or whatever you see periodically.
Thank you, David. Few people remember David Bowie's first album, but it was the foundation for everything that came next. Let us also revisit the foundation of Elasticsearch so we can see how we get to our next destination. In the beginning, Elasticsearch was primarily used for enterprise search use cases like product catalog search. These are generally smaller data sets that are periodically updated with content as assortments and seasons change. In order to have data stored safely, Elasticsearch can replicate data from primary shards to one or more replica shards. If a node holding a primary shard should fail, one of the replica shards can take over the role as the primary shard. This is also a mechanism to scale out search, since search workloads can be executed against the replica shards. You also get increased search throughput by adding more replicas. Elasticsearch can also scale the capacity of an index by sharding it into multiple shards, as shown here in the middle. This type of scaling scales both indexing and search throughput. Today, Elasticsearch is used for a wide variety of use cases, including observability, security, and enterprise search use cases. These have very different performance requirements, ranging from some needing very high indexing and search throughput, and others needing very low latency search. So let's move on. Elasticsearch is highly scalable and generally scales well by adding nodes to the cluster. Adding more nodes, Elasticsearch will automatically rebalance shards across the new nodes in the cluster, ensuring that you can utilize the added capacity. But even so, there are challenges to overcome. If you think of it from an infrastructure perspective, as you add more data to your cluster, the infrastructure has to grow with it. A node with local disks can only hold so much data. And for observability and security use cases, we also partition data by time by adding more indices. Data accumulates over time. Users can actively purge old data, for instance, using index lifecycle management to set up a retention policy. But in all use cases, data is valuable, and in many of them, old data is also very valuable. For instance, in order to find root causes of an incident that happened some time back. Consider an OS patch that introduced a problem that went unnoticed for a while, or the need to audit system privilege changes. Admins have been faced with a tough choice to make, a trade-off of cost versus how much data to retain.
So, as we move on into Act 2, David Bower's album, The Young Americans, was a stepping stone away from his Ziggy Stardust roots and signaled the maturity of the scope, the depth, and the variety of his work. And so likewise, Elasticsearch introduced data tiering, or ILM, and this marked the start of thinking about how we manage extensive data sets for extended periods of time. Now, this is where we talk about data tiering and ILM. The goal of data tiering was to introduce mechanisms that help to retain data for longer and reduce the costs of retaining that data. And in a number of these use cases, the ability to access the most recent data as quickly as possible is critical. So knowing the CPU ticks of a compute node for the last 15 minutes or last 24 hours can be critical to understanding what's happening right now. But there is a period of time where that level of access is no longer required. So this is where Elasticsearch introduced data tiering to help manage this life cycle. Initially as hot and warm tiers, and with cold and frozen tiers being added from version 7.10 in November 2020. Now, data can be tiered from hot all the way to frozen, and this means that different infrastructure can be used for slower CPUs or object stores versus faster SSDs or the fastest CPUs. Data can be managed under a policy, and that will automatically move data down through the tiers. For example, move data after 7 days or 30 days. The policy essentially governs what percentage of data is stored on each tier. And for the search experience, the data tiering is transparent. The same search still executes, and the request is passed to the appropriate tier. And this allows users to build the right type of infrastructure to meet the cost demands of each use case. So if you need to retain data and still have it searchable, for example, for an audit use case, Elasticsearch provides a simple way to achieve that goal. Now, data tiering also provided some additional benefits over and above the automated policies. Snapshots, for example, are held in the object store for cold and frozen tiers, and they're searchable, but they're not mutable. And this is a key difference between the hot, warm, and cold and frozen tiers. These two tiers have no specific replicas, which also saves on storage costs. As you can see in the frozen tier, we just have the local cache. These snapshots can also be, I beg your pardon, cold data is also fully cached on the node local disk, and frozen is partially cached. So this latter scheme gives you a storage saving of 80% over the hot tier, and the former storage scheme, cold, gives you a storage saving of 40% on average over the hot tier. Now, these snapshots can also be from prior versions of Elasticsearch. So data could be created in a 7x line of Elasticsearch, and 8.0 can still search that actual data. So that means you don't have to pull any kind of schema upgrades to the data. And again, this simplifies your data management lifecycle. So this is a huge advantage and allows for more aggressive archival of data with snapshots.
So David Bowie's Low album laid the foundation for the rest of his career by re-architecting the soundscape. In the same way, Stateless is a fundamental change of the Elasticsearch architecture, while still in most ways the same product. This is probably the largest architectural change we've done to Elasticsearch since it was initially released. But before we talk about Stateless, let us revisit a few of the challenges with the existing architecture. And let us start with how data is indexed into Elasticsearch. Today, the primary shard first receives the data and indexes it by parsing the JSON document, analyzing the fields, generating index structures into Lucene segments, writing the translog, and so forth. This requires CPU and IOPS to process. Similarly, the replicas will do similar work, also needing both CPU and IOPS to process. This multiplies the CPU and IOPS needs by the number of data copies that you have. And in order to have resilience, you need at least 2 data copies. Each data node in the cluster also handles both indexing and search workloads. This means that nodes must be sized to handle the peak of each of these workloads in combination. Also, for low latency search use cases, having indexing and search happening on the same node can disturb the search latencies that you want to have. This leads to infrastructure over-provisioning. That is, infrastructure that is repeating work that has already been done elsewhere in the cluster, or infrastructure that is underutilized some or most of the time. One way to help reduce costs is by using ILM and data tiers. About 13% of cloud customers, Elastic Cloud customers, utilize data tiers. The challenge here is one of complexity. Users are required to think about lifecycle, retention, when to move data between tiers, sizing of the data tiers. Getting the right performance versus cost trade-off here is difficult. Also, data has to move from nodes in one tier to nodes in the next tier. And while Elasticsearch will seamlessly move the data around, there's still cost associated to such sharp movements. So let us dive into Stateless. A central principle in Stateless is to separate compute from storage. We utilize object stores as the primary storage of all data. We see the object store here at the bottom with the Elasticsearch nodes above it. Examples of object stores is Amazon S3, Google Cloud Storage, or Azure Blob Storage. Also, indexing and search workloads are separated in this architecture, illustrated here with the indexing tier on the left side and the search tier on the right side. This means that the index and search tier can be scaled individually such that they can each be right-sized for the job. Also, the index and search tier can utilize different hardware, so you can pick hardware that is optimal for the workload. On the indexing side, an indexing node will own all indexing into a shard. And once it's done the indexing, it will push the segments into the object store. We will also push the translog into the object store. The translog allows us to do fast acknowledgement of writes back to clients. And by also putting that into the object store, we have all data stored in a single resilient place. Search nodes will pull data from the object store in order to search it. You may have noticed the local cache just below the search node on the right side. So whenever we fetch data from the object store, we will also put it into the local cache. And by caching it, we avoid repeatedly going to the object store to fetch data in order to search it. This ensures that we can still get great search performance out of this architecture. This is actually similar to how we handle the existing frozen tier in the existing architecture today. Similarly, the indexing tier will do caching as well, depending on the type of indexing. append-only versus update workloads will have different caching needs, but there's caching here as well in order to ensure adequate indexing performance. So we've effectively separated indexing from search with no real data being transferred directly between the tiers even. And we can almost see that there's very little risk of performance interference between these two tiers. Also note now how the indexing workload only has to happen once on the indexing tier. There's no need to run a replication process that would consume additional CPU and IOPS once more, because the resilience of data is already safely handled by the object store. Also notice that there's no state on any of the nodes. There's only caches, and we consider the caches ephemeral. This is hence the name Stateless of this project. This is also important in the same way as we talked about already, in that if one of the nodes should fail, well, data is still safely stored in the object store. Also, we note here that there's no data tiers. Instead, as data ages, the percentage of data that we cache will be lowered automatically, hence getting that older data will be cheaper than newer data. Shards do not have to move around in order to get these cost savings, because actually shrinking the amount of data that we cache can be done in place on the same node. Finally, modern object stores are essentially limitless, so we should be able to handle indexing and search of even very large data sets in this architecture. We are super excited about this ongoing project and to be able to talk to our users, community, and customers about it. This is the fundamental change of the Elasticsearch architecture, and you should expect to see more technical blog posts from us on this subject.
So, after this stateless project, are we done? Well, the answer is no. And like David Bowie, we think we're becoming heroes now. We know that this album is a musical icon, and for many it represents the quintessential David Bowie, and it shows how he evolved his music based on this new musical architecture from the Low album. And the serverless offering that we're going to be coming up likewise is going to be the next set of changes we're planning for Elasticsearch. The stateless architecture that Henning just described is going to be the foundation of this future serverless offering. But why serverless? And more importantly, what do we at Elastic mean by serverless? Well, to meet the needs of the Elasticsearch users, it is critical that we reduce the administrative burden. Right now, you still need to think about sizing, monitoring, provisioning, and upgrades. Now, rather than think about infrastructure or the topology of a cluster or data tiering policies, our vision is to create an endpoint that you can interact with. That could be for data ingest, search, or any kind of other services. This means providing a fully managed service. And behind that endpoint, the elasticity of compute and storage is managed on your behalf by us. So whether you're using our solutions such as enterprise search, observability, security, or the Elasticsearch APIs directly, it's just there. It just works regardless of the data or the searches you throw at it. The endpoint also provides you with encapsulation away from the Elasticsearch version you're using, which also means no more upgrades. These are all handled behind the scenes on your behalf. Now, technically, this is all going to be managed on a Kubernetes control plane using extensions allowing Elasticsearch to run natively in this environment. And looking even further ahead, eventually we want to provide multi-tenancy options which further reduce the cost of the infrastructure for all users. Now, this is a lot of work, and you'll be hearing a lot about this in the coming months. So to recap, our aim is to provide you with a modern platform for near real-time insights powered by search. It will cope with whatever data volumes you have and provide a consistent experience with zero administration. You'll not need to think upfront about how much capacity you need to ingest, search, or store. The system will scale automatically up and down for compute and with limitless storage. It will also be super cost efficient for you. You'll only pay for what you use and not for compute resources that may be sitting idle. So now we've opened up the hood of the engine. I hope you're excited about this innovation as we are at Elastic. Thank you for your time attending this session, and hopefully you've got some questions for us in the Q&A that we've got in our minutes left.
So if you raise your hands, there we have the first question. This is mic number 1, just in case.
Hi, thank you to share the insights here. I have one question. What are the requirements for the object store to survive this?
You can answer that one.
What are the requirements of the object store?
So the requirements to the object store. So because there will be heavy searches running into it, and I mean, maybe the cloud providers can handle it, but if we have an object store on-prem, we need to know how this should scale.
Yeah, so far we've been focused on the cloud object stores that we know about. There's free, Google Cloud Storage, Azure Blob Storage are the free that we also run, the free cloud providers that we run in today as well. And what will the future requirements be? I think that's tough to say, but we need something that works like those cloud providers, blob stores, meaning latencies in the range of 20 to 15 milliseconds for smaller blobs and like, but that's a very detailed discussion to get into. But generally, cloud providers, object stores are infinitely scalable in many ways, right? You can, if you prefix your data correctly, you can actually get very high bandwidth from it. It's only the latency that is a problem, but we do need certain latencies in order to operate well.
Hi. As I understand, this is in the roadmap to come, right? So should we expect this, for example, on EC version 4, or what's the expectation over here?
So if I had that correctly, is it generally when will this be available and on what platform? Yeah, so we're still working through, we don't have an exact release date that we can provide you with today. I can tell you that the Stateless project, we actually ran a POC through this year where we were proving out the separation of the layers, the S3 work. That's all proven successful. So we know that the foundational architectural elements of all of this are acceptable to us, and we'll be going forward with that. In terms of the platform or where it's going to be available, we're focused 100% at the moment on making this work in the Elastic Cloud Service. And then once we've made a success of that, then that's when we'll be thinking about potentially other channels. So I'm sorry, I can't give you much more information at the moment, but it will definitely be available in Elastic Cloud first.
Hi there, I have a question too. How can I use this feature in kind of an existing cluster? Do I have to, will this be a setting in the index lifecycle management, or do I have to spin up a new cluster from scratch and migrate the data? Is there any, what are the ideas there?
Yeah, so as I said, it's going to be available first of all in Elastic Cloud. It will be available as a separate option. So at a very basic level, we envisage that you'll have the Elastic Cloud services that you have today, where you can provision and have more of an administration experience. And there will also be the serverless version next to it that you can choose from. In terms of the migration, we're thinking about potentially snapshots or something like that at the moment.
We've got several options in the play there, but I think that, like, going into those in details now would also like commit us to one of them, and I don't want to do that, but there's several migration options in play that we'll think about, but yeah, we're still in early stages and we're focusing on the product and not the migration right now.
There was one question over there somewhere. Not anymore, then we go here. I was here already.
Hi there. First of all, thanks for this beautiful presentation. I have a question. Maybe it's a little early for that, but I'm just wondering, that model that pay of what you use or pay as you go, if we can call it, do you have an idea how it's going to be scaled? I mean, Is it about the rate of data that are going to be ingested, about the volume that eventually are going to be stored? Combination of these are going to be different tiers? I mean, I can have a million questions, but again, maybe it's a bit early for that. Thank you.
Yeah, so again, on the question of pricing, we know we want to do something that's not resource-based. It will be something like some form of consumption-based pricing. Unfortunately, we don't have the exact dimensions and parameters around that we can share with you at the moment, but it will be something like that. But I'm sorry, I can't provide you any more information at the moment.
Any other questions? I'm winning it.
Yes, regarding the automatic upgrades, isn't it problematic if you want to test something in isolation before an upgrade?
So upgrades will be fully managed by Elastic in this new serverless world. We think we should think of it more as any other SaaS offering, right? So whenever any SaaS product you use is upgraded, it goes unnoticed. But there's a lot of work into that statement, right? There's things around backwards compatibility and ensuring that things work and that you don't see any problems in us doing so, right? And we are undertaking that work. The specific form of that work is still being developed, still being designed, but it's definitely things we are very aware of.
That's the last one.
Thanks. Hi. So is there a co-living stateful and stateless version of Elastic in long terms, or stateless will totally replace stateful?
So stateful, or node-to-node replication, as we like to call it, will stick around. I mean, we have no plans to sunset it at this time. Will we ever? I don't know, but there's no current plans to sunset node-to-node replication. That's going to stick around. So existing Elasticsearch will continue to work, and we'll also continue to develop the existing Elasticsearch architecture. Yeah.
So, thank you very much, Henning and David. It was an honor to have you on stage. I'm very sorry Denmark only made 0-0 today. I would have loved to have better news for you, but at least you got a point. Thank you.